Okay, I think we'll get started as it is officially 7 o'clock. Um, you can hear us, Bart, right?
Absolutely.
Perfect, and we can hear you. Thank you so much, everyone, for coming to this special installment of our lecture series. This very special installment is in celebration of our telescope's 102nd birthday. So we figured a talk on the history of telescopes would be in order. And our lecturer today, as you notice, is not actually here in Cornell, because Bart is actually the founder and the current president of the Antique Telescope Society. He is the recipient of the ATS's Isaac Newton Medal for Meritorious Service to the Society, and as the recognized authority on the history of telescopes, he has lectured for several decades across the US, Europe, UK, Ireland, and Canada. He has over 30 published articles that can be found in Sky and Telescope magazine, the Journal of the Antique Telescope Society, Eyepiece newsletter of the Amateur Astronomers Association, and numerous other journals and publications. He is an avid observational astronomer, and we are super lucky to have him here to speak on his expertise on telescopes. Before he gets started, a quick note, if anyone on Zoom wants to ask questions at any time, you can just put them in the chat to either myself, Jillian Epstein, or Bart. And if anyone in person wants to ask questions, we will do them verbally at the end. Thank you so much, and I will hand it off to you.
Well, thank you, Jillian and Eric, for inviting me. I really appreciate it. I've been up to Fuertes Observatory once, and the Antique Telescope Society is going to be visiting there on I think the 11th of November. So I can't wait to get back. One of your illustrious alumni, actually, I think recommended me to give this talk, and that's Mike Roman, who's been an Antique Telescope Society member for quite some time. So my thanks goes out to him too. Also, I want to thank you all for showing up on a Friday night. I can think of things that I would rather be doing on a Friday night when I was in college, like hitting the bars or getting ready for tomorrow's Cornell-Bucknell football game, right? Or you might be out searching for the comet. Has anybody in the audience seen the comet? Great. Look at that. I haven't seen it yet. I've just been too busy. But I'm told it looks pretty good. So let's get started since I'm holding you up on a Friday night. I've given this talk for about 30 years now, off and on, and it has evolved as new knowledge has come to light. Now you say, well, the telescope's been around 400 years. How is it that we're just now getting more new knowledge? But in fact, the internet has really helped that, of course. Many journals and books that are hundreds of years old are now scanned and available to study, and we've gotten a lot of new knowledge. So there's one other thing I want to mention. Behind me on my screen, let me go this way, is another telescope that is a 12.5-inch Brashear refractor on a Warner and Swasey mount, not unlike Irv. And I'm glad, by the way, you guys are on a first name basis with your telescope. That's fabulous. This one happened to have been originally at Ohio State University. It's the Macmillan refractor. And in the 1970s, they gave it away. Long story short, it is currently being restored professionally and will go into Brooklyn on top of a 4-story building. They're raising $30 million and they're going to have a 30-foot dome up on that building. So these old refractors are really great, and it's wonderful that they're still appreciated, as is yours, I know. So now, the history of the telescope, at least according to me. It's an interesting concept. And let's get the controls going. There we go. All right. So if you think about it, before the telescope, we essentially knew nothing. All we knew was that there were points of light in the sky, right? It was as if we're sitting in a room with windows, but the windows are perennially covered. We have no knowledge other than points of light in the sky. The sun goes across, the moon goes across, and one or two faint fuzzy things can be seen if you were out in the desert in Arabia or something. But we knew nothing about where we were, really nothing. So what did we have? We had mythology and just some vague concepts. And every now and then a comet would show up, and they would be portents of doom, right? We all know about that. So before the telescope, if you think about it, we really just had no concept of what was happening in the universe. Now, after the telescope, we now know almost everything. Of course, with James Webb giving us a lot of new information lately, everything we thought we knew is being questioned again. And this, as you'll find out, is very typical about the history of the telescope. Every time we come up with a bigger, better, newer telescope, it tends to turn astronomy on its ear. And but this, from my point of view, is sort of evidence that the telescope is really the most important invention we ever had. Yeah, fire was good. It lets us cook and keeps us warm. And the wheel was pretty good. That lets us move our telescopes around when they get too heavy. But if you think about what the telescope has done for mankind and our understanding of who we are in the universe, it's a hard argument to work against the telescope. Socrates himself said, we got to rise above the earth to the top of the atmosphere and beyond. Only thus will we fully understand the world in which he lives. So before there was glass, there were crystals. And crystals, of course, occur naturally. And humans have known about crystals really, since they've become humans and found them laying about and found that they were curiously clear. So with crystals, along came gemstones, and the lapidary art was learned by the ancients. So jewels have always been prized, and the ability to take a stone and polish it to a high degree and shape and shininess has been around a long time, and it's been prized. Also, back around 470 BC, the Chinese learned how to make mirrors, and they wrote about concave mirrors to focus the sun's rays. Oops, I think I went the wrong way. Let's go back. There we go. 423 BC, Aristophanes made his famous burning glass. He writes about the use of the burning glass in a play called The Clouds. So we have record of ancient lenses. In the 5th century BC, artifacts that could be lenses were found in a cave in Mount Ida, Crete. Here's one called the Nimrud lens, around 700 BCE. I have seen this. It's actually on display in the British Museum. So if you're in London, go to the British Museum and you can see it for yourself and decide whether you think this is actually a polished lens. It is biconvex piece of glass, actually a piece of crystal. So here's the beautiful thing about telescopes. All you need with a telescope is sand and basically heat, right? With sand and heat, we have discovered our place in the universe because most glass is made simply of silicates, melted silicates. Soda lime glass, which is Coke bottle glass or window glass, is basically just melted sand with some soda and some lime in it. And once we figured out how to control the process of making glass, then the game starts. Boy, this control system is not so good. Bear with me. I apologize, but I'm having some, there we go. Okay, let's try that. All right, so we go from the Nimrud lens to the modern lens. And again, now the technology is that we know how to make them out of glass. So let's dispel a myth about glass. You guys all took physics, chemistry, and somewhere along the line, I'm guessing you were told that glass is a slow moving, super cooled liquid. Raise your hand if that's what you've heard and that's what you've been taught. Is anybody? Yeah, okay, good. So that's baloney. Not only does glass not flow over time in any measurable or perceptible way, it does not sag permanently. Glass is an amorphous crystalline solid, right? And there are articles about that. If you don't believe me, quick take a snapshot of the screen. I'll leave it up for a moment. You can go to that website and get the skinny on glass. So I like to I like to tell people this because almost every lecture I give, everybody insists that glass is a slow moving liquid, but that's not true. So we get rid of one myth already. So along around 4 BC, Seneca the Younger describes magnification by a globe filled with water. Letters, however small and indistinct, are seen enlarged. Now, you've all also seen a droplet of water, maybe on a leaf or on some object where you look through that little droplet of water and you see magnification. So the idea that spherical surfaces that are clear can refract and magnify was known for a long, long time. But nobody put two and two together, and we were still far away from having anything resembling a telescope. But the presentation of the optical principle of at least the reflecting telescope goes all the way back to Catoptrics of Hero of Alexandria from the first century in the Christian era. And he demonstrated that a curved parabolic mirror is the first time we see the concept of parabolas in optics, focus parallel incoming rays, creating an image. However, we don't have any evidence that Hero actually built anything. So he gets credit for the concept, but he didn't make the first telescope. He could have, but he didn't. There is a rumor of the burning of the Roman fleet in 212 BC. Legend of the fleet at Syracuse through the use of specially directed mirrors. I think that's been disproven, but it's interesting that the concept that it might have happened was known. Just the idea that you could concentrate enough heat with a mirror large enough. And this is supposedly how it was done. So Pliny the Elder comes on and says, and yet we find that globular glass vessels filled with water, when brought in contact with the rays of the sun, become heated to such a degree as to cause articles of clothing to ignite. I can tell you this is true. I have ignited some of my own articles of clothing using a Herschel wedge on my telescope and not paying attention to where the vast majority of the heated light hit me. So if you ever use a Herschel wedge, don't burn yourself. And I know you've got one in the observatory. I think that's the first astronomer. So now, if we look at a timeline, just on the history of science and civilization, we had the Greeks, then we had the Romans in the 5th century, right? And then all the way up to the 16th century, nothing happened. We had the Dark Ages. There's no science. We're completely blind. But really, did modern civilization rise from nothing? No, of course not. That's just bad historical education. By 984, we had a fellow named Ibn Sal who completed a treatise on burning mirrors and lenses, describing plano-convex and biconvex lenses, parabolic and ellipsoidal mirrors. So now we're starting to get somewhere here. We're getting past the, gee, we know that this stuff does something, to descriptions of how it works. This is from his text. Then we came across in 1289, so long before 1600. There's a Florentine manuscript documenting the use of lenses to correct the vision of the elderly. These are the first eyeglasses. And there's a painting from the early 14th century showing one what must be the first painting ever of someone wearing glasses. And the name lens is derived from the similarity in shape with the lentil bean, ventri lentice. This is that painting or manuscript. So that's the first known image of optical glass being used. But by 1450 to 1500, concave lenses were developed by lens makers. That technique to produce concave lenses. Convex lenses were pretty easy to make, but to make a good, accurate concave lens was much more difficult. So now we have everything in place to create both the Keplerian and Galilean telescope. We have all the technology. We've got glass or crystal, and many lenses were made of crystal and not glass. And we have the technology, the lapidary and polishing technology to make both concave and convex surfaces. So long time between before the Christian era, all the way up till the mid 16th or 15th century, just to get to that point. So things weren't moving too quickly. Now, we had a bunch of people in that era at that point all decide to start figuring out how to take the concept of eyeglasses and make something where we could see something far away. And they all had concepts about how to do it. Leonardo da Vinci wrote about it. Roger Bacon supposedly tried to make a reflecting telescope. Leonard Digges actually did make some rudimentary instruments where supposedly he could see things at a distance through a reflection. And then we have an Italian named Giambattista della Porta in 1593 who wrote about his invention, so to speak, of a optical tube where he could see things with it. But if he made one, if he ever made it, none exist. There's no record of anybody ever looking through it. He talks about it in a conceptual way, but there is absolutely no written record or any corroborating evidence that he was successful. And then later on, he even discusses the fact that it was really a trifle, more like a toy that he played with, and it really wasn't very good. It's questionable whether it even magnified or not. Okay, now that's 1593. On September 25th, 1608, in Middelburg, Holland, a local lens maker writes, well, he writes to the States General in Holland, Prince Maurits, and says, I'd like to show you something that I've invented. And he's granted an audience, and they go up on top of the tower at the State House, and there are other people there, and he pulls out this tube, and they use the tube to look at a church steeple in the next town over. And they could see the windows and the clock in that church tower with his invention. I don't know that he even had a name for it. If he did, we don't know what he called it. This is the only known image of this fellow from Middelburg, Holland. His name was Hans Lippershey, not Lippershey, it's Lippershey. He was actually German by birth, and he immigrated to Holland, and he brought his eyeglass business with him. So he made spectacles, eyeglasses. The top image here is the only known drawing of what his telescope supposedly looked like. And the bottom is a representation of that drawing, a more modern representation. It was a simple thing. It had a sliding tube inside another tube. It had a biconcave eyepiece and a biconcave objective. This is what he showed, and he asked for a patent. And Prince Moritz looked at it and pawned it off on a committee to discuss whether he should get a patent. And they decided no, it was too simple. And by then, after a couple of days, other people came forward and said, oh, no, we've done this too. We've got one of these, or we can make one for you. So, we want the patent. Well, he didn't get the patent. Instead, there was a request. They said, we'd like you to make some more of these. And in fact, we want you to put two of them together and make us a pair of binoculars. Now, it wasn't enough just to invent the telescope. He invented or made the first pair of binoculars as well. And so they also paid him 900 guilders, which was a lot of money. He bought a new house and he upgraded his business, and he started making and selling these tubes. And he lived very well. And that's almost all that we really know about him, except that he was a pious man, humble guy. And we know when he died. We don't even know exactly when he was born. So Lippershey called it supposedly his kijker, simply his viewer or looker. Others were to call it a Dutch trunk or an optic tube or a perspective tube. So the name telescope wasn't around yet. That's the only other supposed image, a painting of Lippershey, but he, in fact, that painting was done like 40 years after Lippershey died, so we don't know how accurate it is. So the thing is self-evident. If anyone had perfected a telescope before Lippershey, could they have kept it a secret? And to what benefit would that be? And I want you to keep that concept in mind, because now there are a lot of people coming forward saying, oh, we made the telescope earlier. We've known about it earlier. There's this Italian guy who said he devised the very same thing. And is it possible that Lippershey heard about it? Yeah. So he didn't get his patent. But almost immediately after he showed it, this handbill, sort of like the newspaper of the day, a little pamphlet, was printed 3 weeks after the meeting with Prince Moritz, or here Prince Maurice, of 10th of September in 1608. And at the very end, after they talk about all the politics and the military stuff and everything that's in this newsletter, there's this simple paragraph. I'm going to read it. A few days before the departure of Spinola from The Hague, an optician from Middelburg offered a few glasses to His Excellence, with which it is possible to see the windows of the church in Leyden. Now, they're in Middelburg, and they could see over to Leyden. The mentioned glasses are very useful to inspect objects at a distance of a mile and further, as if they are very nearby. And here's the best part. And even the stars, which do not ordinarily appear to our sight and to our eyes for their smallness and weakness of our sight, can be seen by means of this instrument. The person who wrote this was there when he demonstrated his kijker, his optic tube. And clearly they used it in the evening to look up or at night to see stars that they could never see before. So not only is it the first telescope, it is the first astronomical observation. This is a really apocryphal event, in the history of mankind. On October 2nd, he submitted his application for the patent. He got his 900 guilders. He was refused. And another fellow demonstrated the same with a similar instrument. And another spectacle maker, Matthias of Alkmaar, got 100 guilders. He put on his own patent application. None of them got a patent. That's actually pretty good because it really expanded the market for telescopes very quickly. So everybody jumps on the bandwagon and starts making telescopes. There's the bandwagon. And in November of 1608, okay, remember, we started in September. 2 months later, Pierre d'Estoile gave a printed account of the Dutch instrument to the English ambassador in Paris. Also, and that's important, you'll see why. And in November, the pamphlet reaches Italian philosopher Paolo Sarpi in Venice, friend of Galileo, most likely via Paris and Jacques Bouvier. So we all know where we're heading with that one in Galileo, right? So he also writes in April of 1609, he passed a shop showing several people glasses of a new invention. This is in Paris, right? He's told the invention was owed to a lunetier or glassmaker in Middelburg in Zealand, and that last year he presented to Prince Maurice. Okay. Now, this is printed in a journal in France by the same fellow, Delatour. And what's important about this is he's telling you that already by the spring of the next year, telescopes were being sold in Paris. Right. So we went from September, the first one, November, all of a sudden everybody kind of wants one. And by April 30th or before, actually, it was actually by early spring, telescopes were being sold on the street. Anybody could walk up. If you had the money, you could buy a telescope. So the idea that telescopes were around before Lippershey, just in my mind, it just doesn't hold any water at all. So between the spring and the summer, Thomas Harriot finds out through that English ambassador who heard about the telescope and got his hands on one. He got one to Thomas Harriot and through the normal trade channels. And Thomas Harriot in England, this gives him a leg up on Galileo. So everybody hears that Galileo was the first astronomer, the first one to make astronomical observations and to discover, for example, craters on the moon. Well, nothing could be further from the truth. And even in Italy, I was just at the Museo Galileo, and I saw on their display that they're claiming that Galileo was the first astronomer. And I grabbed one of their curators and said, I cry foul here. You guys got to go do your homework and check out Thomas Harriot, right? Because Harriot was looking at the moon in July of 1609 and drawing the moon and predated Galileo. This is Harriot's drawing from 5 July, I think. I'm sorry, July 26th, 1609. Not a very good drawing. He didn't have a great telescope, but he certainly saw the Terminator. You can see how rough it is. That's this, I think you can see my laser pointer there. That's this line here, and stuff was going on here. So he couldn't really see a lot, but he certainly was trying to observe the moon with his first telescope. He also made the first observations of sunspots in 1610. And in 1611, Galileo and Scheiner started their sunspot observations. So Harriot gets credit and should get credit for being the first solar astronomer, not Galileo and not Scheiner. Now, today, Harriot's, Galileo's, and Scheiner's observations are being analyzed as part of a program to produce a complete view of sunspot activity since the telescope's development. This is the longest running scientific experiment in history, the sunspot cycle study. Oops, there we'll get it. Okay, there we go. So that's Harriet, supposedly. And those are his 1610 or 1611 sunspot drawings. Looks like January 19th. So Harriet fabricated, collected, and distributed and used many telescopes. All of them were Galilean style. And see, Galileo, he gets his name on the telescope, even though Harriet was making them before him. And they don't call it the Lippershey telescope. They call it the Galilean telescope. He did improve it. He made better telescopes, some of them magnifying up to 30 or 40 times. Whereas Harriet's telescopes magnified about 6 to 10 times. Harriet didn't actually make them. His assistant, Christopher Tooke, made them. And so, in theory, we consider Tooke England's first telescope maker. But Harriet knew of Galileo's works, certainly. They corresponded. He read Galileo's works. And by April 1609, 3-powered spyglasses could be bought in spectacle makers' shops, Pont-Neuf in Paris. And they were being sold a couple months later in Italy. So, like I said, you could get them anywhere, but Galileo certainly made the best. So, what he didn't do, he didn't invent the telescope. Everybody thinks that. A lot of people think that. He did not make the first observations with a telescope. He didn't even call it a telescope. So, Galileo, I'll tell you, he's a great promoter, but he gets credit for a lot of stuff he didn't do. However, by 1609, he did make his first telescope. This is what it supposedly looked like. And it's about a 20-power instrument. This is on display at the same Museo Galileo. If you get to Florence, you don't want to miss that museum. It's fantastic. And what he did do, well, he published Sidereus Nuncius. He published much better drawings of the moon, of course. He also noticed that Venus had phases. And for that, he almost got burned at the stake, right? Which actually isn't really true. You know, Galileo's problem was not with the church per se because of he was following the Copernican theory. It was really because he was bad politically with Pope and just aggravated them and all the bishops and cardinals. Really so much wasn't what he said, it was how he said it. He was told not to publish and he published anyway. So I've seen this drawing firsthand. This is Galileo's handwritten chart of the positions of 4 of the bright moons of Jupiter. He didn't initially understand that they were moons. He thought they were stars, but he noticed they were following Jupiter. And over a period of several months, he charted their positions and deduced quite correctly that Jupiter had moons. And he also adroitly named them the Medicean moons after the guy who was paying his bills, the Archduke of Medici. That got overturned eventually. And now we call them fondly the Galilean moons. So all holy hell breaks loose. For had the device any known historical provenance, the astronomers of Europe would not have been so amazed and perplexed and delighted with what they discovered with their newly contrived cylinders. So this is Professor Alan Chapman from Oxford, basically saying, look, the thing is self-evident. If there had been a telescope before Lippershey, no matter what all these claims are, Where are they? What happened? Nothing happened. But Lippershey comes along, and now all the scientists see what Galileo did with it, and everybody wants one. Oops. That should do it. There we go. So now, at a banquet honoring Galileo, since he showed that there are moons going around Jupiter and kind of proving that the Earth was not the center of the solar system, he's very famous. And a Prince Federico Sessi in Italy gives him a big banquet, and they proclaim the Dutch instrument be called by the Greek name teleskopos, which was coined by John de Domitiani, a Greek court mathematician. So that's where the name telescope came from. So the thing's moving along at this point like wildfire. And by within 6 years, okay, is that right? 5 years, 5 years, a telescope shows up in Japan and was presented to Tycoon Ieyasu. Within 5 years of its invention, it makes it around the world and shows up in Japan. You can see these court ladies using their little spyglass. I don't know what they're looking at. They're looking at ships at sea, I guess. I don't know what she has in her pipe there. So everybody wants one. This is a big thematic hint, right? Okay. Eccentric Joe K. That's Johannes Kepler. The eccentricity, of course, is a pun. Kepler figured out what Copernicus could not, and what Tycho could not, which was that orbits are not circular, they are elliptical. And that answered a lot of questions. He was able to do it not so much because he was using a telescope, he did it mathematically and just with a lot of deduction. However, he did take a look at Galileo's telescope and he analyzed it and he thought, that's good, but there's another way to skin that cat. And all of a sudden, he comes up with a better design. The Galilean telescope, which is not too different from the Lippershey Kuiper, it differs in that the eye end has a convex and concave piece of glass, whereas Lippershey had biconvex at the eye end. Now, so what happens here? Kepler's design gives you a wider field of view because he puts the eyepiece back past the focal plane and he uses a plano convex lens as an eyepiece. Gives you a wider field, gives you better eye relief, gives you the option of higher magnification. But interestingly, it flips everything upside down and flips everything left to right. So if you've ever looked through Irv at Fuertes without a diagonal, everything is backwards. If you put the diagonal in, now it's correct north to south, but it's still flipped left to right. And if you put in a correcting diagonal that flips it both ways, you're looking at it the way you would see through a Galilean telescope. Okay. Moving right along. Nope, I didn't get it. Okay, good. So Christopher Scheiner, he's using Galileo's telescope to study sunspots. And this is his very early records. And he was a real scientist. His drawings are impeccable. His notes are great in sort of the true German tradition, really thorough. and great at keeping records. Everybody wants one. So this begins the great game of leapfrog, which is what we have over a 400-year period, right? So this concept of leapfrogging is the problem is every time you improve the telescope, there are new discoveries. And all the people using the new improved telescope, they come up with these discoveries. Now they come back to the telescope makers and say, listen, this is great, but we're all out of gas here. We need a bigger, better telescope. So the telescope makers go to work and they try and come up with a bigger, better telescope. And then everybody wants one of those. The problem is making a telescope is a very difficult thing. And you couldn't always get one. The other problem is in order to make them better, which in this case means higher magnification. And we're not yet into the era of big aperture. But what we're looking for is more magnification. You have to make them longer. Okay, so we all know the fundamental function of magnification with a telescope. You just divide the focal length of the eyepiece into the focal length of the telescope, and that's your magnification. So if you're kind of limited in your eyepieces, if you want to get a lot of magnification, you end up with something like this. This was called an aerial telescope. This is probably the largest one ever made. Some of them are only 6 or 8 feet long, 10 feet long, 12 feet long, but they were so long you really couldn't make a tube that would support the telescope without sagging. So you ran into not only optical issues, but now you start running into mechanical issues of telescope making. Supporting this thing was a wonderment unto itself. However, there are some people today and members of the Antique Telescope Society who make these and use them just for kicks and show really fine images that they get, because another fundamental advantage of a very long telescope, besides high magnification, is you get better color correction out of a single element lens. If you have really long focal length, when you get to the focal plane, most of the colors are very close to the focal plane. So that was one way of dealing with chromatic aberration. Now, not everybody wants one. Why would that be? Well, astronomical uses for the telescope. Okay, measuring stars, mapping for navigation, mapping for timekeeping, mapping for calendars. But this requires more accurate telescope, but it also required a better way of making measurements. So not only did people want better telescopes, but what they also wanted was a better way of using the telescopes. So the history of the telescope is also the history of some other technologies that made the telescopes useful. Anybody know what we're looking at on the top? That should be kind of obvious. Raise your hand if you know what that is. Nobody knows. Okay, one person knows. Okay, it's a vernier. Okay, and it's a vernier that allows you to divide the tick marks on the bottom by the tick mark into tenths. Okay, so you've increased the accuracy of your scale on the bottom by tenfold by using the vernier. The vernier scale originated in ancient China, but it was reinvented in its modern form in 1631, not long after the telescope, because there's a demand now for a vernier, right? French mathematician Pierre Vernier. I I incorrectly used the English. It's actually Vernier. Also, another thing that you want to do, you want to measure things side to side, the split, the difference in position. So you need a micrometer. This lies at the heart of astronomical measurement down to the 20th century, right? You couldn't measure anything accurately without a micrometer. And with the micrometer, you can measure, for example, accurately double stars. And you can measure their position angle as well if you put a circle on it. and you see the bottom one has a circle. And then with that circle, if you had a vernier, you were really in good shape. So while the telescope is being improved, instruments are also being improved. So the micrometer was invented in 1639, but he died also right about the same time the vernier came about. But he died in battle at age 32. His invention was kind of forgotten until Azu published his version in 1667. So let this be a lesson, publish or perish, so to speak, right? So there's Azu, and everybody wants a micrometer once he comes out with his version, and we find micrometers all over the place after that. Now, let's stop with the refractors for a minute. In 1616, a guy named Zucchi describes a reflector and proceeds to tell kind of absolutely nobody. He does write about it, but not really. And another fella, Caravaggi at Bologna, before 1626, worked on a reflecting telescope, and he passed the technique to a certain Giovanni. Now, before we get to Giovanni, Zucchi did make one unit, but he didn't like it. He didn't think it was very good. He couldn't really test his mirror very well, and he just kind of put it aside and forgot about it. Caravaggi, however, he passed his information along. So the concept of the reflecting telescope and a few crude mirror reflectors were known to Caravaggi, Giovanni, another fellow, Marsili, and to Galileo. But these were poor spherical mirrors, and the idea languished for a while until we come across a guy named Bonaventura Cavalieri. Also, another fellow named Marin Mersenne and James Gregory, and another Frenchman, Laurent Cassegrain, all describe catadioptric reflectors. And this is in the 1600s, but nobody could make one. It's one thing to describe them mathematically, but it's another thing to be able to make it. And by the way, you see the name Gregory and you see the name Cassegrain. So Gregory gets his name on the Gregorian reflector. Cassegrain gets his name on the Cassegrain reflector. Interestingly, neither of them were the first ones to design it, and neither of them could even make one. But they published better. There was also some politics. Cassegrain, after he developed his reflector, it got squelched by Newton. Newton didn't like that. So Cavalieri, he designs his quote unquote Newtonian reflector, I think about, let's see, 1632, right? That's about 30 years before Newton came out with the Newtonian reflector. Now look at that picture. This is Cavalieri's picture. What do you see? You see a typical standard Newtonian reflector, a primary, spherical primary, a flat optical secondary pointing out to an eyepiece on the side. This is what Newton showed to the Royal Astronomical Society, the Royal Society, and what he got tremendous credit for. I think he won the Copley Medal, even though he didn't invent it. And I'm fairly sure that you can bet that he was aware of Cavalieri's work. So here's Isaac, Sir Isaac. It's interesting how they show him with an apple breaking light apart instead of a prism. That's a conundrum, isn't it? So in 1660s, Newton concludes that it's impossible to make a lens that can refract all colors to a single focus. One of his great mistakes, by the way, of which he's made a number of them. So in 1668, he perfects his version of the reflector. This one works well, and he gets all the credit and sets back. This is interesting. He sets back refracting lens design by half a century because of his mistake. So what happens? We don't have refractors. We got reflectors in the early 17th century. It's the golden age of the Gregorian reflector, or making up for Newton's mistake. And everybody wants one. So there are any number of optical shops in London, in England, in Scotland, in Italy, in France that start making Gregorian reflectors. This is a reflector made by Ramsden, Honest Jesse Ramsden. You'll hear that name again. Beautiful workmanship. I've seen that. Now, that brings us back to Newton and the lens and his mistake. There's a guy in England named Chester Moore Hall, of which we don't know a lot about. We know that he was a lawyer, he was a landowner. He did go to Cambridge. He was really a brilliant mathematician, but as an amateur, he was a polymath. But again, he didn't need to make money. He had a lot of land. He did work for a short time as a lawyer, but then he gave that up and just tended to his investments and his properties. But he was very much interested in optics, and he was interested in the idea that the eye, which is a lens system, could correct for chromatic aberration. And when you look at the moon naked eye, you don't see a halo of blue around it, do you? So he said, well, if the eye can correct for chromatic aberration, what's to say that a lens system can't do the same thing? And he got to work on the problem, and he realized that you could select two different types of glass and shape them to work together to bring at least two of the three primary colors of glass to a focus, and the third primary color very nearly to a focus. So Moore Hall designs the first doublet achromatic lens in 1733. Okay. So he's taking all the colors and bringing them. He's got red and green at perfect focus and blue slightly off. That's in lateral chromatic aberration. Longitudinal chromatic aberration. The achromat is correcting for blue and red together and green off. And somewhere in the middle there is a focal plane that gives you a pretty damn good image. And it's an improvement over single element telescopes. Big improvement. So what did he do? Well, not a lot. That's the problem. In the intervening years between 758, he took his idea to two different lens makers. He asked one to make one element and another to make the other element. And he figured he'd pick them up and take them home and play with his new invention. But they were both busy, and they farmed their work out to a third optical shop who got the job at the same time to make two elements the same diameter with matching internal curves, and figured out immediately that they were supposed to go together, and figured out what Chester Moore Hall was doing. So his idea of keeping it a secret went right out the window. And this is really one of the great stories of patent law, because in 1758, John Dolland, who kind of knew what was going on and heard about this thing, he gets to work to develop his own glass and lenses, and he comes up with a slightly different version of a two-element achromat, and he goes for a patent, which the lawyer, Chester Moore Hall, never bothered to do because he couldn't care less really about making telescopes. He did approach one telescope maker about getting them into production, but that guy died, and it languished, and it just never happened. So Bass, he's the one that knew about what was going on with the two pieces of glass. Klingenstierna in Sweden independently came up with the same math earlier than John Dolland. And there was a big fight. There was a huge patent fight. Dolland was given the patent, but there was a lawsuit from the Worshipful uh, on a worshipful company of spectacle makers of London, the trades union. They fought to break the patent because they all knew about it before Dahlin did it. And some of them were actually making them. So here's the judge. I swear that's him. And he came up with a landmark. He told them all to bugger off. He came up with a landmark decision. Okay. The landmark decision was, and this is where the word scrutoire was in my earlier slide. He said, it's not for the person who first did it. It's for the person who brought it out for the public good. He said, the person who develops the idea but locks it up in his scrutoire, his writing desk, does not deserve the patent. So he threw any claims for Chestermore Hall out the window. He told the spectacle makers they had to pay Dollins the fees, and what you have is a lot of them at that point starting to fake the Dollin name on their own telescopes to get around the patent. There was fraud going on very early on. Telescopes were big business in those days. Every ship had one or five, right? Now, this comes to another point about the history of the telescope. The problem is glass. So in order to make a good achromat, you have to have good glass. And good glass was hard to get. And if you wanted a bigger achromat, you needed bigger pieces of good glass. When you make glass, you get bubbles, you get seeds or little pieces of dirt, and you get inhomogeneity in the glass. And all this stuff shows up in the image. So every telescope and lens maker is after the best glass they could get. And all over the world, there were only a handful of companies making what was considered optical glass. There were one or two in Italy. There were one or two in France. There was one in England. So there were, let's say, five, maybe six companies that could make decent glass, but they couldn't make them in sizes that were appreciably large. So if you could get glass to make, let's say, a 5-inch lens, you were ahead of the game. You could sell that telescope. You could write your own price for that telescope because astronomers who wanted to make discoveries needed bigger, better telescopes. We all know what telescope size counts, right? Of course. So making good glass was a problem. Pierre-Louis Guinan, he worked at this for 35 years. He was by the way, he was a clockmaker, but he decided to try and make good glass because he also was a lens grinder and he couldn't get good glass. So the problem is you got to stir the glass. Now glass is like thin bubble gum when it's molten. It's like a heavy syrup. What you want to do to get rid of the homogeneity is you want to stir this glass as it slowly cools. And you stir it so that it's really homogeneous. That pulls the bubbles up to the top, which you'll cut out later, and all the seeds float up to the top, and you have really good glass from the middle to the bottom. But here's the but. What do you stir it with? It's 1200 degrees C, and it's cooling. But what do you stir? You can't stir with a wooden stirring spoon, right? And if you stir it with an iron rod, you introduce impurities from the iron or the iron oxide and any other thing that happens to be in that iron. And you end up discoloring the glass. So what you see in old glass is that clear glass was typically very green. Now, somewhere in Italy, they figured this out in Murano, the island of Murano near Venice, because they were known for a particular glass called Cristallo. Nobody knows how they made it at the time, but you couldn't get anything bigger than a 2 or 3 inch lens, so it didn't really matter. I think they were adding lead. Frankly, they were making lead crystal. So what he develops is he figures, well, okay, the iron rod is strong enough and it'll hold up to stir the glass right to the end until it gets too thick. But if we coat it with the same stuff that we line the pot that we've melted the glass in, We can protect the glass from the iron itself. So he came up with the fire clay stirring rod in 1805. And that was a huge invention because that allowed telescopes to really bloom in size. Um, this is Guinan. His invention was so good, Fraunhofer hired him to teach him how to do it at Benedictine in Germany. There's Joseph Fraunhofer. We think of Fraunhofer as being a huge spectroscopist, but he was also one of the world's greatest telescope makers and lens makers. There's his spectroscopic work on the right, but the telescope on the left, does anybody know which telescope that is? It's a hugely famous telescope for two reasons. It's the Dorpat refractor. It's in Tartu in Estonia. Struve, the older Struve, Otto Struve, used this telescope to measure about, I think, 9,000 double stars, leading the world by far in cataloging double stars. But even more importantly, Fraunhofer developed what we now know today as the German equatorial mount, which was a huge improvement on working with big telescopes because it was balanced. You could see all parts of the sky with it, and you can put circles on it to make measurements of your position. And it was basically a real game changer. We use it today. Is a German equatorial mount, right? Almost every telescope you buy that's not huge is available on a German equatorial mount. So what that did, now we get everything we need. We have bigger, better telescopes. We have reflectors if you want them, which have perfect color correction, by the way. And we have bigger refractors, which are really giving us razor sharp images because the opticians are getting good glass now. And we have micrometers to measure, and we've got circles that are accurately divided and using verniers for positional astronomy. So it's not any, oh, we also have what? Spectroscopy, right? And Fraunhofer. So it's no longer about where. It's no longer just positional astronomy. Now the telescope is being used to tell us what. This is Sir William Herschel. That's his second largest telescope, his 20-foot reflector that he set up in Bath, England. And what did he do? Well, he started measuring the universe and mapping all the stuff that wasn't stars with that reflector. That's the first significant, really important reflecting telescope. It was a game changer. It was so far bigger and better than anything that came before it that he was able to get knighted, and he also found what did he find? Uranus. Discovered Uranus with it. So now we get big mirrors, bigger results, but a big drawback. What do you make the mirrors out of? Okay. We couldn't make glass mirrors then. Well, we could make glass mirrors, but they weren't shiny. It was just glass. We had nothing to coat them with at that time. So the shiniest material that we knew of was something called speculum metal, also known as bell metal. And it's mostly copper. You add some tin and you throw in a little arsenic, which killed one or two telescope makers over the years who made their own. And you can make big metal mirrors. Now, two problems with that. Speculum metal is only about 60% reflective at its best. And it's got an awful coefficient of thermal expansion. So it takes a long time to cool down to achieve its optimal shape. The other thing is it tends to tarnish. So you have to be able to repolish it periodically and be able to test it. This was kind of an advantage for Herschel, for William and his son John Herschel, because they made their own telescopes and used them, but they also sold them. So they had a lot of business repolishing their mirrors too. Oh, let me go back to that telescope just for a second. Forgive me. Oops, that didn't work. One more time here. The telescope you're looking at, not that one. This one. That's the Leviathan of Parsonstown. That telescope exists today. It was rebuilt in the early 1990s. I know the guy who rebuilt it, Mike Tuberty. He's an engineer, and it's owned by the 7th Earl of Ross. It was built by the 3rd Earl of Ross. And I have actually used that telescope. I climbed up the ladder on the left side, and you go up this ladder with one spindly little handrail, and then you walk up on this, out on this arched walkway, and then when you get to the top, there's a gangplank that you walk out on, and you're up about 4 stories high, and then you got to lean over empty space and look through an eyepiece that's about the size of a coffee can at night in the dark with no moon, ideally. And I got to tell you, that's the hairiest telescope I have ever looked through. But I did see some stars, and I'm one of the few people that can say they've actually used this telescope. I don't know that I would get up there again. So this is the Great Refractor in Harvard. So it was the largest refractor in the world when it was installed as a 15-inch. Telescopes are getting bigger, they're getting better. This is the next large refractor, I think, was at the Naval Observatory. It's still there. That's a 26-inch made by the Clarks. The 15-inch was made by Mertz and Mahler in Germany, and the Clarks, of course, were Americans. So now we're getting record-setting telescopes one after the other. They can't make them big enough, fast enough, culminating in really the golden age of astronomy. This is the 40-inch refractor at Yerkes. I've had the pleasure of looking through that as well. That's still operable. It's now an educational consortium. The University of Chicago finally sold it off. So what happened to the reflectors? I mean, we had the Gregorian reflectors, and then we had some bigger, better reflectors made by Herschel, and then culminating in the 72-inch Leviathan, the largest telescope in the world. And then we don't hear much about reflectors and reflector technology. But along comes another physicist, kind of just like the spectroscopist, whose name now escapes me. But we have Leon Foucault, French physicist. And he hears about this new technique of putting silver on glass. And in the, let's see, the 1850s, the technique was known since the 1830s, but in the 1850s, and it was really sort of part of the technology of photography. But Foucault comes along and says, you know what, we can put silver on glass. And he was also known for his testing theory. We'll get to that in a second, but he perfects silvering on glass along with Steinheil in Germany, and that changes everything, right? So, but his Foucault test, the other thing he's known for in telescope making history, is how to test for a parabolic curve scientifically, as opposed to empirically by grinding and polishing and then testing it on a star and then going back and trying to figure out where the zones are and the errors are and what the problems are. That was all trial and error, trial and error, trial and error. slow, tedious process that not too many telescope makers were good at. But he came along with an objective method, no pun intended, to analyze the really the diffraction pattern, or the wavefront of a reflection of a mirror, and figure out where the problems were, uh, and map it out on the mirror itself. So then you could correct it very easily once you knew exactly where the highs and lows of the mirror were and how far off of a parabola you might be. And if you had a turned edge, for example. So at this point, these are all the things that are starting to happen starting in the 1850s. We have spectroscopy from Fraunhofer was the name I was looking for. We have photography, which is already around. We have photometry, measuring how bright something is. Right now, there were visual photometers designed in that era, but with photography, we also had photographic photometry. And with spectroscopy married with photography, we got spectrographs. And then a little later on, the concept of interferometry was developed, really perfected by, the American physicist, whose name also is escaping me. We'll get to him. And bolometry, the study of heat. These all demanded bigger, better telescopes, especially reflectors, because one of the problems with refractors, besides the fact that you don't get all the colors focused properly, you also get some absorption of light in the glass itself, and it's selective absorption. It's not 100% smooth absorption. So that makes spectroscopy a little funny. It makes bolometry a little bit funny. And so there's a demand now for bigger and better reflectors, especially since Herschel and astronomers that came after him saw all these big, faint, fuzzy things, and they want to know what's going on. So in 1816, let's see. I'm sorry, in 1839, we have the perfection of the photographic camera, right? And the first photo of the moon is taken by Louis Daguerre, but it disappeared because it burned up in a fire. But we know that Daguerre took a picture of the moon. By 1840, John Draper in New York, Dr. Draper at NYU, and he started doing astrophotography. This is his image of the moon. It still exists. It's, I think, in the New York Historical Society archives, or it might be at the Draper Museum at Hastings-on-Hudson. So we have a shift in the paradigm from refractors to reflectors at this point. Why? Well, it's the new astronomy, really. That's what it was called, astrophysics, right? Along comes a guy in Pittsburgh. You'll recognize the name. Anybody know who that is? He made the lens on your telescope. That's John Brashear, Uncle John. And he perfected early in his career silvering on glass better than what Foucault did. Silvering on glass was a real problem because it was fulminate of nitric acid was part of the process, and it's explosive. And every now and then, telescope makers were blowing themselves or their laboratories up. It's really touchy stuff. Think nitroglycerin touchy, right? You shake it the wrong way, you look at it the wrong way. Brashear blew up his office one time because of it. So using it is tricky, but he figured out a way to use it where you do not have to heat the solution, and it was a much easier, faster method and much safer method. I mean, it's still dangerous, but they stopped blowing themselves up. And so he was known for the Brashear method of silvering, which was in place and the go-to method for 50 years, up until John Strong and vacuum aluminizing. So Uncle John, you guys should all sing his praises since he made a really nice lens for you. Now, Mirrors have no problems with color. There are no issues of absorption. The glass is easier to make because you don't have to worry about light going through it. Mirrors can now be resilvered when they tarnish. They could be made in much shorter focal lengths, and larger diameters are easier and cheaper. I mean, really big diameters. Brashear rivaled the world's largest telescope, which was still the world's largest telescope up until, I think, 1917, when he finished the 72-inch reflector for Dominion Observatory in Canada, in Victoria, British Columbia. So that Leviathan was the largest telescope for like 60 or 70 years. The second most important reflector after Herschel's reflector really was one that doesn't get enough credit. A couple of mirrors were made for a guy in England named Common, and he made the mirrors, he sold them, and he sold them to a guy named Crosley. Crosley built the reflector on the left. He used it for a little while and then decided he didn't want it anymore. And he ended up selling both mirrors. He had two, so he could keep one silvered or get one silvered while the other one was being used. And he sent the mirrors, one of them, to the new observatory in Mount Hamilton in California, Lick Observatory, with its 36-inch refractor, but it was also a 36-inch mirror. So now they had two 36-inch telescopes. The problem Lick had was they had a jerk for a director, a guy named Holden. Holden didn't really want to have anything to do with that silly reflector. He didn't think it was any good. They couldn't get any results out of it. And they were all about publishing results and justifying their existence and their budget. So a guy named James Keeler, who was originally in Pittsburgh, and he was a graduate of Johns Hopkins. He was a brilliant, brilliant spectroscopist, probably the best spectroscopist in the world. He was a good friend of John Brashear's. He rebuilt the telescope entirely, and that's what you see in the bottom right. That is the Crossley reflector as it is today. And I got to tell you, it's a death trap. People fall down in that pit and get hurt because they stand up on this platform that you can see behind the telescope, and the platform moves around. And if you lean over and fall in, good luck. You're there by yourself, alone at night, and nobody's going to come save you. But it was a really important reflector because he did all kinds of great spectroscopy with it, and he published paper after paper. It got to the point where he actually ended up being the next director at Lick after Holden left. That's how good Keeler was. Unfortunately, he died not long thereafter, very young. This fellow, does anybody know who that might be? Probably not. That's John Strong, the physicist. He also cut his teeth at Johns Hopkins. And one of the things he was known for is ruling diffraction gratings for doing diffraction spectroscopy with Henry Rowland's ruling machines. But he was asked at one point to silver some prisms for some physics experiment. And but they said, maybe we could do something with aluminum. And he experimented with vacuum aluminizing, which was a brand new technology. And he got good results aluminizing these prisms. And they thought, wait a minute, why are we messing around with silver on glass that tarnishes and we got to resilver it all the time? Aluminum is just as shiny or almost as shiny. And it's shinier in areas of the spectrum we like. Not so much in the red, but in all the other colors, it's a lot better. And it's really hard and durable, and it's cheap and easy. So he makes and experiments. He makes a larger vacuum aluminizing chamber and aluminizes a mirror. And then he goes to town. He goes to talk to a guy he knows very well, George Ellery Hale, who is busy building Mount Wilson Observatory. And he talks him into building a very large aluminizing chamber and they illuminized the 60-inch at Mount Wilson and the 100-inch at Mount Wilson. And they're really successful at it. They put another illuminizing chamber in for the 72-inch in Dominion, and it revolutionized large reflectors. And every observatory today with a large reflector pretty much has an illuminizing chamber on site.
Before you keep going, I just want to acknowledge that we're a little over time. So
I'm
if
almost done.
anyone needs to go, that's completely okay. Thank you so much for coming, but I'm not going to cut you off. You can keep going.
Okay, well, we're almost done. So this is the newer age, another new astronomy, and it really opens up the door for big, large reflectors and pretty much brings us to where we are today. But I do want to point out that the other new thing that came along was Carl Jansky and radio astronomy in 1932. So that's an often overlooked part of the history of the telescope, are radio telescopes, right? And a guy who gets not enough credit is Grote Reber, who made the first parabolic dish in his backyard when he was a kid in Wheaton, Illinois. He was an overachiever. And during World War II, he couldn't get a job in the military because of his German background. So he had basically radio astronomy to himself, and he mapped the radio galaxy and invented the science of radio astronomy. I don't know if he got the Nobel Prize, but if he didn't, it's a crying shame. Now that all bets are off. How big can you make a telescope? We have the Palomar, which had a new type of glass, borosilicate or Pyrex, and so no more window plate glass. That was a huge modern step in the right direction. So we get this leapfrogging. Here's a classic example. In infrared space telescopes, we had Ys, and the image on the left is the best that we could do, but it wasn't good enough. So astronomers go back to NASA and say, we need a better infrared telescope because we can't see through the dust. So they come up with Spitzer. Now all of a sudden, look at the difference in resolution, the number of stars that you can see, but it's still blurry. They didn't like it, right? Now, what do we have? Well, the one on the right, you should all recognize as one of the first images that came out of the James Webb Space Telescope. All three are the same field of view. And all three are because astronomers keep pushing telescope making and instrumentation technology to continually improve. You get a better telescope, then you discover stuff. Now you want another telescope, bigger, you leapfrog. Then you make more discoveries. And that's the name of the game in the history of telescope making, really from day one. You astronomers are never satisfied, let's face it. and rightly so. That's probably as good a place as any. So behold the telescope, that greatest of inventions, flings open the gates to our universe, and we shall know ourselves better when we dare to explore. And I thank you for listening, and I'm happy to take questions.
Thank you so much for giving this talk. That was extremely interesting. If anyone in the room has questions, just raise your hand and I'll bring the microphone over to you. And if anyone on Zoom has questions, you can just put them in the chat and we will read them off. Any questions in here? Okay, I will give the chat a look. But I think we are good to go. Let's give Bart one more round of applause.